Hi everyone, in this video we are going to talk about the ideal gas equation of state. This video will be the last video for chapter 2. What is the equation of state? The equation of state is an equation that relates pressure, temperature and specific volume of a substance. So as long as the equation relates these three properties, they can be called an equation of state. So what is the ideal gas equation of state? So for the ideal gas, you have this equation, PV equals MRT. I think you have seen this equation before. Okay, so let's see what each of these terms are. P is pressure, stated in kPa, kilopascal. V is volume, meter cube. M is mass in kilograms. Then we have T is temperature in Kelvin. And finally, R is the gas constant. And the unit that we will use in this subject is kilojoules per kg K. Alright, now the gas constant is a constant derived from this equation. Okay, R here equals to Ru, which is the universal gas constant. It's a fixed value divided by the molar mass. If you recall from your subject structures and properties of materials, molar mass is unique for each substance. So for example, oxygen will have its own molar mass and CO2 will have its own molar mass. Nitrogen will have its own molar mass, etc. Okay, so you have different values of gas constants. So this information can be found in table A1 and A2. So you can pause this video to check out table A1 and A2. You'll see these values in the gas constant column. Okay, there are a lot of other substances as well. All right. So before we proceed any further, it's important to understand what actually is an ideal gas. Okay, so it's actually a theoretical gas. It's a theoretical concept. Okay, as you know that all gases are real. Any gas at all that exists on this earth are real gases. So this theoretical gas is when we assume that the gases have elastic collision between the atoms. That means when the atoms of the gas collide with each other, the collision is elastic. Elastic means they bounce back. They do not absorb any of the energy from the collision. Okay, the next one is they have no intermolecular forces between them. So also in structures, you've learned that between molecules, there may be intermolecular forces of attraction that binds the molecules together. So in the concept of ideal gas, we assume that there are none of these. Okay, when can we actually use the ideal gas theory? Okay, it is when real gases have low density. Okay, for example, at low pressure and high temperature, gases will have low densities. Therefore, only in this situation, we can treat them as ideal gas and we can use the ideal gas equation. Okay, but to make things simple for you, in this subject, you can use the ideal gas equation anytime at all where you see ideal gas as the substance in the system. Okay, as long as it's an ideal gas, be it CO2 or oxygen or nitrogen or air, you can use the ideal gas equation. However, you can't use it when you are dealing with vapor. So be it water vapor or refrigerant vapor, either saturated or superheated vapor, you cannot use the ideal gas equation. Okay, the reason is because vapor has high density. You can in fact even see the particles, right? You can see steam, okay, but you can't see non-colored gas. So that is the difference. We can only use it for low density gases. So you've seen the equation. How do we use it? Right, so this is the equation. And to use this equation is quite simple. If you want to determine any parameter in this equation, there are 5 parameters. You just need to have the other four parameters. For example, if you want to determine temperature here, you just need to know what's P, V, M, and R, and then you can determine T. Okay, another way that we can use this equation is when you want to determine the change between two states. For example, we have some gas in a tank. Maybe it's heated. Okay, it's heated until it reaches state 2. So in this case, we can determine the relation between the two states. So obviously state 1 will have its own properties. Okay, P1, V1, T1, M1, and R1. And state 2, after going through the process, will have its own properties. Yeah, so note that between the states, there can be some properties that are similar. For example, in this case, ideal gas constant, of course, is similar. For example, let's say this is oxygen. It will have a certain value of R. And in state 2, it is still oxygen. So it will have the same value of R as in state 1. Therefore, R1 equals to R2 equals to R. We just simplify it and call it R because it's the same gas. Now, you rearrange this equation for each state. You will have for state 1 as R equals to P1 V1 over M1 T1, and you will have the same for state 2. And because we have established that R is the same, therefore it makes this term and this term actually the same. So you can equate them here. Okay, so this is the relation between two states. Now, we can simplify this further. If any parameter in the equation is constant, they can be cancelled from the equation to simplify. For example, let's say pressure in state 1 is equals to pressure in state 2 here. So their magnitude will be the same. For example, 100 kPa each. Yeah, so this is 100, this is 100. So you can easily just cancel it from the equation because it will not change the equation in any way. So if more parameters are constant, for example, in a closed system like this, mass should be constant. So if mass is constant, you can remove mass from the equation as well. And then you have a very simplified version. Okay, so that is how you use the ideal gas equation, either to find one parameter when you have the other four, but also when you have a change in state, when you have a process going on, you can use the relation like this. Let us go through this example. The pressure gauge on a 2.5 meter cube oxygen tank reads 500 kPa. Determine the amount of oxygen in the tank if the temperature is 28 degrees and the atmospheric pressure is 97 kPa. So here we have a tank. It's filled with oxygen gas. The tank has a volume of 2.5 meter cube. It has a temperature of 28 degrees and the gauge pressure, if you recall, gauge pressure reads 500 kPa. Okay, now we can write down the values. I welcome you to pause the video and try to work this out yourself. Okay, so write down all the information. PG is 500. We have PATM here. It's given as 97 kPa. So we need to find the amount. And amount here refers to mass. Yeah, when you see amount, it's never volume because volume can change. Volume can be compressed and expanded, whereas mass is fixed. So when you see amount in thermodynamics, it's always mass. So to find the mass, we have the ideal gas equation, and then we rearrange to find mass and see, do we have all this information? P is, we need to use the absolute pressure. I've not mentioned that yet. Okay, P in the ideal gas equation has to be the absolute pressure. Therefore, you need to add gauge pressure plus atmospheric pressure. Okay, what else? Temperature has to be in Kelvin. So 28 degrees plus 273. And then we have a volume. Volume is straightforward. You just take this value, 2.5 meter cube. And gas constant R, this is from table A1. Yeah, make sure you find it for oxygen. This should be the value. So you substitute all this into the equation and you solve to get mass. Yeah, where this should be the final answer. So in this case, we do not have a process happening. We have a static state where you just have to find one parameter when you have all the other four parameters. Okay. Now, okay, the next question here is your quiz for this week, for week 3. You can try it out. You can take time. You can ask me some questions if you don't understand. And the hint here is first you can sketch the system first. Okay, you will see that the system has 2 tanks. Yeah, you have a 1 meter cube tank here connected through a valve to another tank. So how does that look? Okay, and label them properly, and you will notice that there will be a process involved. When the valve is opened, the valve between the tank is open and the system is allowed to reach thermal equilibrium, which means that the whole system now, both tanks, will reach the same temperature of 20 degrees. Okay, what you have to find is the volume of the second tank and the final pressure of air. Final means after the system has, the 2 tanks has mixed together and reached equilibrium. What will be the final pressure? Okay, so good luck with this and I'll see you in the next video.